This is Physics 2120, Lecture 17, and today we're going to talk about Faraday's Law and Lenz's Law. Now, Michael Faraday was an experimental physicist who lived in the early 1800s, and he had lots of contributions to electricity, including the invention of the motor, the generator, and the transformer. He came up with the laws of electrolysis, and more importantly, he came up with electromagnetic induction. An induced current is produced by a changing magnetic field, and there is an induced EMF associated with the induced current. You cannot produce a current without a battery present in the circuit, but Faraday's law of induction describes how we can induce an EMF. So the experiment is as follows. Let's consider a loop of wire that's hooked up to an ammeter so we can measure the current flowing in the wire. When a magnet is moved toward the loop, the ammeter deflects, which means that there is current going through the loop. When the magnet is held stationary, there's no deflection in the ammeter, and so there is no induced current. Even though the magnet is near or even inside the loop, if it's stationary, there's no current. And when it is moved away from the loop, the ammeter deflects in the opposite direction so that we know the current is moving in the opposite direction from when the magnet was moving towards the loop. So, an ammeter deflects when a magnet is moving toward or away from the loop. The magnetar also deflects when the loop is moved toward or away from the magnet. So therefore, the loop detects that a magnet is moving relative to it. And we relate this detection to a change in the magnetic field. So this is the induced current that is produced by an induced EMF. So Faraday's experiment, he took a primary coil, which was connected to a switch in a battery, and the wire is wrapped around an iron ring. Now this wire is insulated, so there's no current going from this primary coil into the iron ring. There's a secondary coil is also wrapped around the iron ring, and there's no battery at all present in the second coil. So the secondary coil is not directly connected in any way to the primary coil. At the instant the switch is closed, the ammeter needle deflects in one direction and then returns to zero. When it's open, the ammeter needle deflects in the opposite direction and then returns to zero. And that ammeter reads zero when there is a steady current or when there is no current in the primary circuit. So an electric field can be induced in a circuit by a changing magnetic field. This would be the current in the secondary circuit of that experimental setup. The induced current exists for a short time only while the magnetic field is changing. We generally express it with this statement: an induced EMF is produced in a secondary circuit by the changing magnetic field. The actual existence of magnetic fields or magnetic flux is not sufficient to produce the EMF. That flux must be changing. And Faraday's law of induction says the induced EMF in a circuit is directly proportional to the time rate of change of the magnetic flux through the circuit, or mathematically, the EMF is equal to the time derivative of the magnetic flux. Now, we remember that phi is the magnetic flux through a circuit, and we find it by integrating B dot dA. If the circuit consists of n loops, all the same area, and if phi sub b is the flux through one loop, the EMF induced in every loop adds up, and Faraday's law becomes E is equal to n times d flux dt, where n is the number of loops. So let's consider a loop enclosing an area A, and it's lying in a uniform magnetic field B. The magnetic flux through that loop we calculated before is B times A times the cosine of the angle between the two. Therefore, the induced EMF is the time rate of change of BA cosine theta. Now then, how can I change the EMF? Any one of those three variables, B, A, or theta, can change in time. So, if I'm changing the strength of the magnetic field, then that would change the flux and therefore would change the EMF. If the area enclosed by the loop is changed, let's say it's made of loose wire and I could fold it together and bring it apart, that also, and A would be changing as a function of time, would induce an EMF. Or the angle between B and the normal of the loop can change in time if the loop were, say, spinning or turning, or any combination of the above. So if both, say, the magnetic field and the angle were changing, I would need to take both of those in consideration and use the chain rule. So it would be dB dt times A cosine theta plus BA sine theta d theta dt. Now there's many devices that use Faraday's law, and one that you see a lot in building code is something called a GFI, or a ground fault indicator. And it's designed to protect users who are using electrical appliances against electrical shock. The current code in the US says that there has to be a GFI in every bathroom and every kitchen and every garage circuits. So, a GFI is used when I have an alternating current circuit. So, the currents in wires 1 and 2 are opposite each other. That just means that as current comes in 2, it comes back out 1. When the return current and the outgoing current are the same, the magnetic field around these two are 0. As we know from Ampere's law that the integral of B dot dA is equal to mu naught times I enclosed. Well, if the currents are the equal and opposite, there's no enclosed current, so there's no magnetic field around this iron ring. However, if some current is coming in and some is going in another place, there will be a net current through this loop. That'll cause a magnetic field to begin around these loops, and that will induce a current in the sensing coil, and the circuit breaker will deduce there's a current and will turn off the whole circuit. Another more musical example is a pickup coil on an electric guitar. So, a coil is placed next to a vibrating string, and it causes a portion of this string here to become magnetized. When the string is moving back and forth, it creates a changing magnetic field in this pickup coil. Usually it's buried inside of the wood of the guitar itself. That changing magnetic field induces a current in the loops, and that change then goes to the amplifier and out to a speaker where you can hear it being played. So let's look at a problem. A coil consists of 200 turns of wire. Each turn is a square of side 18 centimeters, and a uniform magnetic field directed perpendicular to the plane of the coil is turned on. If the field changes linearly from 0 to 0.5 teslas in 0.8 seconds, what's the magnitude of the induced EMF in the coil while the field is changing? So we'll start with Faraday's law. The magnitude of the EMF is just the change in flux with respect to time. In this case, we have several turns of wire, and so there'll be the same EMF in every turn, so the EMF over the whole coil is N times d flux dt. Now, the change in flux is just the change in B times A. Well, the area is constant, it's just L squared, so it's just the change in the magnetic field. So the change in flux with respect to time is just delta B over delta T times L squared. So the EMF then is going to be 200 turns times a change of 0.5 Tesla in 0.8 seconds times 18 centimeters squared, and we get 4.1 volts. Now, another voltage that we can induce is something called motional EMF. And this happens when a conductor is moving through a constant magnetic field. Say I have this piece of metal here and it's moving through this magnetic field N. As I move this conductor through the field, the different charges experience a force as it's moving through. It's the same that F equals QV cross B, and it's directed along the length of this wire, or this bar. So under the influence of this force, the electrons move to the lower end of the conductor and accumulate there. And as a result of the charge separation, there's an electric field that's produced inside the conductor. And the charges then accumulate at both ends of the conductor until they're in equilibrium with regard to the electric and magnetic forces. For equilibrium to occur, the electric force, QE, has got to equal the magnetic force, QVB, or the electric field induced is equal to velocity times the magnetic field strength. So if there's electric field in the bar, that means there's a potential difference is maintained between the ends of the conductor as long as the conductor continues to move through the uniform magnetic field. If we reverse the direction, the polarity of the potential difference is also reversed. So for example, I could have a sliding conducting bar in a uniform magnetic field. If I can redraw this as the circuit where I have this resistor over here, and the sliding bar becomes an electromotive force just like a battery would be, and the magnitude of it is BL times V. We're going to assume the bar has zero resistance. Therefore, the work done by the applied force that's causing this bar to move appears as internal energy in the resistor. The induced EMF, right, is d flux dt, and so the flux is BL times X. So B and L, the length of the thing, aren't changing, so the only thing that's changing is dx dt, where x is the width of the loop, and dx dt is just the velocity, so the induced EMF is BLV. And since the resistance in the circuit is R, the current from Ohm's law is E over R is just BLV over R. The applied force has to do work on the conducting bar to get it to move. This moves the charges through the magnetic field. The change in energy of the system during some time interval must equal the transfer of energy into the system by work. So the power input is equal to the rate at which energy is delivered to the resistor. Power, we know, is the applied force times the velocity, which is ILB times V. And the power we also know is E squared over R. I could also just have a metal bar rotating in a magnetic field. So, we have one of length L, it's rotating with a constant angular speed omega about a pivot at one end. And a uniform magnetic field B is directed perpendicular to the plane of motion. Let's find the potential difference between the ends of the bar. Well, the first thing we know is that the velocity at any small part of this bar is R times omega, where R is the distance from the pivot point to the place where I'm interested in. So, the little bit of EMF induced along this part of the bar is BV times the length of it, which was dr. But V is R omega, so it's BR omega dr. To get the total EMF along the whole bar then, just integrate. So it's the integral of BR omega dr. B and omega are constants, they come out. And I integrate R dr from 0 to L, the length of the bar. So the EMF of this rotating bar is 1/2 B omega L squared. Now, a German physicist named Heinrich Lenz came up with a way of determining the direction of the field. So Faraday's law indicated that the induced EMF and the change in flux have opposite algebraic signs. And it had a physical interpretation. We now know that as Lenz's law. Lenz's law states the induced current in a loop is in the direction that creates a magnetic field that opposes the change in magnetic flux through the area enclosed by the loop. In other words, the induced current tends to keep the original magnetic flux through the circuit from changing. So for example, let's say I have a loop, and it moves through an area, the shaded area, that there's a magnetic field present. Right. So we want to plot as functions of x the flux through the loop, the induced EMF, and the external force required to counteract the magnetic force to keep the velocity constant. So first, the flux. As the loop is coming in from the side, as it starts to enter the magnetic field, the flux through it was 0 before and now is increasing until the loop is completely in the field. And once it's completely in the field, the flux is no longer changing. Now, while the loop is moving through the magnetic field, there's some flux, but it's no longer changing. And then as it exits, the magnetic flux in the loop goes down linearly, and then as it's out, it's 0 again. So we know that the EMF is equal to BLV when there's a changing magnetic flux. So there is no EMF as the flux is not changing. As it's changing, we get a constant EMF of minus BLV. And then as it's all the way in, it's 0. And then as it's leaving, as the flux is changing in the opposite direction, we get an EMF with the opposite polarity. So the force required to keep this moving is going to be B squared L squared V over R, and there's no force required, and as it's moving into it, there's a lot of force that's required, and then once it's all the way in, there's 0 force required to keep it moving again. It will just slide along. But as soon as it starts leaving the field, we have a force to keep it moving in this constant direction. So, to review what we talked about today, Faraday's law states that there's an induced EMF whenever you have a changing magnetic field going through a loop. And Lenz's law stated that the direction of the change is the direction of the current in the loop is such that it tries to keep the magnetic flux constant in the loop.